I can see it. Yes. Thank you.
I won't be very long. Thank you very much, everybody, for being here. Hope you are all safe and confined. Using the opportunity to participate to webinars like this, for which we don't always have the opportunity. So thank you also very much to Jesper, who was at the initial point of this webinar. So what I will say will be relatively short. I will explain to you in a few words the principles of the software Jesper has been using, Lunar, which is a development by my company, CADLM. We are specializing in various machine learning and model fusion, model reduction technology, in particular for applications of optimization, reliability, and robustness. We have a handful of OEMs and a lot of tier one companies who are now exploiting our technology, and it is an expanding domain. So I think we will be hearing about this more and more. What is important about this particular technology? Why is it different from the ones we already have? Well, you all know the finite element solutions and everything we have at hand as a tool for analysis. Very efficient, but low performance in terms of CPU. We can't do always what we want to do, enough runs which we would like to run. And of course, with the energy issues going up, there are more and more constraints on just long-running CPUs and DOEs and stuff which we used to do 10 years ago, but we have to be very careful about these days. Another solution is going down on dimensional aspect, so reducing the scale of the problem to 0D, 1D, etc. And there are also newcomers into the market via data mining and solutions that are similar to that. So our platform, Odyssey, is actually in the middle. So we combine all these three technologies. We can say that we do actually use all three. And the main advantage of this is that we are completely independent of the solver technology. We can apply this technique, Odyssey technique, to any technology, since it is very, very horizontal, and it is applicable to many industries, automotive, aeronautic, biomechanics, etc., etc. Motorsport, as Jesper will show you. The idea behind what we do is relatively simple. It's a sort of surrogate modeling, but which goes beyond what we know today under response surface modeling. The idea is that we learn from previous runs, CAE runs, and then we transform them into sort of compressed databases, which allows us to have some predictive solutions, and then we employ those. These could be also in turn combined with real sensor technology, so it opens the path to anything you know about digital twins and combination of real and virtual data. The main idea being that by learning, we want to replace that middle square here, which is the most time-consuming part of the analysis, going from CAD to modeling, from modeling to solver, and in cases where you need to iterate, well, this is very costly. The idea here is that we just link directly the parameter or variable set or unknowns of a system to a set of responses. We skip the middle part, and from that, by repeating these, we just learn how that middle part functions. We actually discovered the differential equation without actually doing it. Why would we do this? Well, there are typically three domains where this is of great interest. The first one, yes.
Sorry about that. Can you please go into presentation mode, Kambiz? On the PPT presentation mode. So
presentation mode. Okay.
Yeah. Thank you.
Is it okay, or do you see two screens?
Yeah, two screens. If you could swap it and yeah.
I'm not always successful in doing that, but Sometimes it works, sometimes it doesn't.
Or we can go back to the previous mode. Yeah, that's fine. That's fine. We can go back to the previous mode. Yeah.
I can go back to the previous one. This one.
Yeah, I think so. Yeah, that's fine. Yeah.
This one is safer actually. It works. Yeah. Okay. So this is the idea. This is the major idea. And as I was saying, if you want to do anything which is related to pre-design stages, you want to have a very fast model, sort of 1D, 0D model, which is a question and answer model for doing parametric studies, trial and error, etc. This is an absolute tool, what we are producing here, presenting here. If you want to do anything related to post-design, optimizing the design, model fitting, etc., this is also a very, very efficient tool. Once you go to certification validation stages, well, of course, you need to think about reliability and robustness. Well, then it becomes a magic tool. And I will explain to you why, because when we are in this left box, we are in the order of 10 runs. When we go into this middle one, we are in the order of 100 runs. Now, when we go to the right one, we are in the order of 1,000. Now, just imagine you can do 1,000 crash simulations in less than an hour. So this is the order of magnitude of what we are talking about, and it makes it very, very interesting. Now, main advantages of this approach are that it is actually a relatively simple known start. We don't change anything in our existing solutions. We just take the model on board, do a DOE. We know how to do a DOE, design of experiment. We change parameters X, we obtain responses Y. So once we have that, we have constituted our database, and the rest is just data mining, reduction techniques. Very important point that we actually need very limited number of runs. It's not like response surfaces where you need to fit to extravagant polynomials. So that is not the case. We exploit very much the eigen modes of the system, and this is more or less limited for physical systems. So it's very few runs. And when I say very few runs, I'm talking something in the order of 2n to n squared maximum. So we are in that range. And being the number of parameters or variables. This is adaptive, so we can add to the system. We just keep on iterating, and we converge more relatively fast. Once we have that, the effort for the additional computing is very limited. Order of seconds. Yeah, here the sort of sled test. I have a picture here on the right. I can't show the video because it was too big. But the one on the right is a finite element. The one on the left is actually Lunar. The one on the left takes something around an hour and a half. The one on the right takes a second. So this means we have the possibility to do hundreds of runs for optimization within just a few seconds. Now, this is not a response surface because we are not handling scalars. We are just handling fields, tensors. So everything which the which the differential equation captured, encapsulated, we can reproduce that, so we can provide time history output, including animations, stress field, etc., etc. And once we have that, then we can start the optimization. I just will show you right away. A final advantage of this, that this technology is very easy to encapsulate. So we can actually couple this with any tool you have today, any optimization tool you have today. You can actually easily link this to, and Jesper, I think, will show you this tool. He has he's using a separate optimization package from Odyssey, just to show you that this is feasible. And to make my presentation, I would just like to mention that there is a trial version of what we are showing here. If you are interested, contact me or just go on that website, which is here. No, it's not here. It's here. Go on that website, and you will find a 1 month free access to our technology. So thank you very much, Hemant and Jesper.
Thanks, Kambiz.
Ball is on your side now.
Jesper is going to detail how Pratt Miller used CADLM technology to implement a suspension design application.
Okay, I should be able to go to full screen at least. So welcome everyone. I'm gonna talk a little bit on how we actually can use Lunar in practical runs. And of course, I'm using Adams, and Adams still runs fairly fast, so we don't get that big improvement. But if you, for example, would be using Ditran, Nastran, Actran, Mark, any non-linear FE tools that takes hours to run a dynamic simulation with, that's when you really would see the performance. But we get really good outcome using Lunar with Adams and other tools that's really not as slow as a full nonlinear FE. So because Adams, of course, as most of you know, is my specialty, that's what I'm focusing on here. So Kambiz already talked about this, that Lunar is a tool for reduced order modeling using relatively few but smart selected points, and it gives you the parameter sensitivity, and it gives you the full time series, not just scalar responses. An overview over the Lunar process with Adams. So you start with running a reduced DOE using Adams Insight. I base this on Insight because it interfaces very easily with Adams and Adams Car. Insight is still a little bit of a Stone Age tool when it comes to DOEs, but in this purpose, it actually works really well. All the methods available in Insight use Latin hypercube, typically what would be recommended. And so once you set it up, you export the workspace, and we're going to call that X here because of terminology and Lunar. Besides your regular Latin hypercube DOE, run an additional 2-3 run sweep. I usually just do an extremity parameter sweep with the lowest values, mid values, high values, and then I gaff the whole DOE with that. Export this workspace as well. This is what we're going to call XN and YN. This is your verification. You could as well add a couple of extra runs to your original DOE and just remove 3 of the data points when it's done and use those for validation. The only important thing with the validation is that it should not be exactly the same points as you used in your original DOE, because of course they will fit perfectly. Now then you export your results, basically the time series you want to look at, and we're going to work initially in this project mainly with vertical acceleration of the vehicle. We call this Y. Should be semicolon or comma separated, so CSV file works good. It could be either row or column oriented. I initially was skeptic to a row orienting, but working with it a bit, I find that easier to get around with. Then you added your 2 exported workspace files and just remove the response columns. So when Lunar sees this, it's going to treat every column as an input, and now you have otherwise a mix between input and outputs. When you run your DOE in Insight, you just add anything as your response because they're scalar responses and they're not really useful in Lunar. But if you want to use it for regular DOE results, please go ahead as well. Then once this is done, let's do all the pre-processing. Start a new Lunar project. You specify your DOE workspace file, the response file, the X and Y. Then you specify your XN, your validation runs, and you're optional to specify a time series. Otherwise, it would just use the number of points for the x-axis when you plot things. You do this, you import the files. Lunar will show all base curves. And it will also, for each line in the validation file, the XM file, Lunar estimates the time response. Then you import your validation responses and compare the curves. That's what you see down to the lower left there. And so in this case, we had 3 rows in the XM file, and we have 3 calculated responses by Adams in the YN, and they're sort of correlating, but not perfect. All depends on how accurate you want to be, and that goes back to how many runs you put into your Latin hypercube, really. After this, you run a Lunar script to determine the best solver setting. This is the Lunar solver setting, not Adams. And you apply those settings and use those for this experiment. That's what you see in the lower right plot there. And you can see that they got quite a bit closer on all 3 in this case. Problem we're going to work with here. We have too much vertical acceleration on the vehicle. Classic military suspension design problem. Run a given road at a given speed, and we should not have more than 6 watt absorbed power at any occupant. So in this case, we're actually, of course, this is a well-developed vehicle that's well in progress, but we're trying to push the envelope on it. We're running, in this case, on an Aberdeen test track. The church will be the heavier of them, 2.97 inches RMS value, I believe it is, on it. And we can see here we have quite a bit of accelerations, get an absorbed power a little bit over 12.5 watts. How I set this up, I select 10 parameters. Of course, it's an existing vehicle. We can't go in and start changing hard points. So mass is given, weight distribution is given. So I'm working with 5 factors for the front and 5 factors for the rear. It's the Young's bumper scale factor, how stiff it is, the clearance to the Young's bumper, and the damper scale in compression and rebound, finally the front spring scale. These are all parameters that's easy accessible from Adams' car using Insight, so it doesn't take much time to set it up. If you will do this traditionally with using a quadratic fit, and this of course is still using Insight. I said it's a little bit Stone Age in that you have to select your fit before, because you select between a linear interaction, quadratic, cubic fit, and that determines how many runs you want to do. A more modern tool would instead use, you can basically select as many points as you want, and then it would use a radial basis function or tweaking functions to fit those. But for a quadratic fit, I think the minimum for 10 parameters is 81 runs, but as normal common sense says you should use 1.7 times the minimum number of runs. You end up a bit over 100 runs. With a cubic fit, get over 250 runs needed. We're only going to run this with 60 runs using the Latin hypercube distribution. So in most cases, and particularly when you get into bigger and bigger projects with more and more factors, Lunar gets more and more efficient compared to a traditional DOE. For typical optimization or DOE, you need factor 10 less than a traditional DOE. And for reliability and robustness, well, we're talking factor of 100 or 1,000 in difference. And not to talk about how the speed gonna change there. So, and then I said, as I also running a 3-level DOE sweep. And the validation run is shown down here. You can see it's just the minimum values corresponding to the minimum value column here. A median value or a mean value and a max value. So it's not this one is not even the nominal values, but just a point in the middle. Then we have a tool written in Python that helps you extract data from Adams runs. It can take a set of files in one directory. This is how Adams Insight will write it out. Just select the same directory here, point to any one of these files. Or you can have the files in different directories with the same name. And then you select as many outputs as you want. And it's going to specify then, well, in this case, I pick time. I always want time out just to have something to plot that I can compare with Adams. And in this case, I only take the vertical acceleration as output. This is the file structure. So to the left, we have our X and XN file structure that can be exported from Adams Insight. There's nothing strange here. You go down there, there's 60 rows with data points here. And to the right is the structure of the Y or YN files. So it's only one channel per file, in this case, vertical acceleration. And again, it has 60 columns. Actually, in this case, it has 59 columns, or sorry, 59 rows, because one of the rounds failed, and I had to go into the in the workspace file and remove that. So this is how my tool there extracts the data. Open up Lunar. So that was all the pre-processing. So open up Lunar, create a project name and directory we want to save it in, and then we specify our X file, parameter set, the channel, which is this case vertical acceleration, the validation file, the XN, which is what I call the reference here, and the time axis. So here you don't involve the YN, the reference results, they come in the next stage. So you tell Lunar to import these files, and it will import them. Shows all the baseline files here as the light blue. The background, there's actually 59 curves there. There's not that much difference between the different curves in this experiment. And then it automatically takes the 3 rows in the reference or XN file and estimates the response to those parameter sets. Next step, here I hide the base curves. Convenient little button for that. And then I import my YN files, or my YN curves, I should say, the 3 responses corresponding to my XN files. And I can see that I color them same, and I can see particularly the blue and the red aren't really that good. The green in the middle is a decent good fit. But from here, I go on and I run this Lunar script I mentioned before to find the best solver fitting. In this case, it came out with an RBF with multi-quadratic solver as the best one. And we see here, looks a little bit better on the page than the page before, but still not perfect. It's a really high frequency signal. We look at one of the peaks here, we can see a pretty good. This is highly zoomed in over one of the peaks here. I believe it's this one, around 5.5 seconds. We have for the mean values, rather good fit, but not so good fit at the extreme values. So that's the problem around working with accelerations. And accelerations, we know, even in Adams, is typically a noisy signal in these cases. Going over, looking at absorbed power, and absorbed power, of course, is a filter integrated version of the acceleration. So we filter away some of it, basically make it suitable for how we measure responses of the human body to accelerations. And then we integrate the output from that filter. So you can see Still a little bit high frequent noise, but the general structure is much, much better. So we extract those data here. Actually, that has to be done through post-processing stage. And we do the same, repeat the same process here. And we get a much better fit. And the best solver in this case is the proper orthogonal directions with the kriging submethod, linear, and third level. This is actually what we're going to work with here. Looking a little bit on absorbed power here, and of course, as I said, absorbed power is directly related to acceleration here. But if we overlay the curves, we can see directly that a single peak, that's a little bit, but really not that much to the acceleration. When you start having areas like this, that's high or low or high absolute value for a longer time, you get pretty distinct or quick rises in the absorbed power. Lunar gives you a very nice advantage here. It actually takes a lot of time to get out from a normal DOE. It's that you can immediately get the parameter effect at any point you want, the sensitivity from all the parameters. In this case, we're looking here at time 7. So just in this area where we have the first big rise here, actually almost a dominant area. And at this case, we can see now that Young's bumper scale, increasing the stiffness on the front Young's bumper, front and rear is bad. It's going to increase our power. But increasing the clearance, both front and rear, will be better. Increasing the damper stiffness in the front is good for us, but decreasing the damper in the rear is bad. And we want to make the spring softer, both front and rear. So that was a quick, easy response. And I can go through the curve and look anywhere I want, or take an interval over this area to specify what sensitivities I want to look at. Very, very useful tool. But that's not the real purpose of this presentation. So now we go into the optimization phase. And Lunar has a direct interface to Nova, which is the CADLM optimizer. And it's very simple. It allows me for quickly specifying which parameters I want to include, where I want to start it, and I can specify a target. In this case, I see the maximum of the curve over the whole interval. And then I click OK and click Run. And in this case, it ran 189 evaluations before it converged. And it only took 53 seconds. That's pretty good. If I would run 189 runs in Adams with this model still runs close to real time. I would say it takes about 35 seconds to run a 20-second simulation on my new laptop. And so you can do the math there, that it would still be some 15 minutes, 20 minutes to run the optimization directly in Adams. The result coming out here is the dark blue curve. I was plotting that together with my base curve just to show that actually the optimized result is quite a bit outside of what's covered by my Latin hypercube distribution. And from that, I draw the conclusion that this is probably a little bit optimistic, because Lunar doesn't really know much about what happens out there. The same thing with in a regular DOE, you would never try to extrapolate from a DOE. So really not that much difference from a DOE in that sense. So be a little skeptic, and always, as always, when you run an optimization or draw conclusions from a DOE or any type of reduced order modeling, always feed it back in and run a verification on it. We put this back into Adams, which is very quick. I actually did it through Adams Insight, as Lunar can export this workspace back out, and I just go back into Insight and say, okay, use this workspace and run it, even if it's just one run. And we can see now in Adams, from the acceleration curve, we have cut quite a bit of the peaks in this. And if we look at absorbed power corresponding to that, yeah, we went down from over 12.5 watts down to 8.9 watt. So 12% more than what Lunar predicted, but that's covered when we're on the edge, or actually even outside of the edge as this. So this is very quick and easy to do directly inside Lunar. And I know Kambiz and his team is working very hard to extend the capabilities of Lunar and Nova in conjunction. But now we're going to see here what happens if we start, well, what happened to the vehicle for other cases, and how can we start constraining this, and how can we, just to show an example on how we can embed Lunar, or really Quasar, the underlying engine, inside any other tool. And this could be potentially embedded in an onboard controller on the vehicle, in a game simulator. We are actually looking on using it in war game simulators, or I should say war game training simulators, where we train operators for different types of robotic vehicles in the military side. So what we can see here now is our baseline was good, but we get lateral acceleration, we lose a little bit, but just peak, the steady state value seems to go to the same. Roll angle is about the same, we get a little bit more, but the roll angle velocity got quite a bit worse. And that's an annoying thing to have, because that really corresponds to lateral head toss when you go into the curve, as your head as a driver or passenger sits quite a bit over the CG. So, or particularly quite a bit above the roll axis of the vehicle. Let us look here on if we go in and put this a constraint on the roll velocity. We start with, say, 7, we want to constrain it to less than 7.5, because that's about where we were originally. Problem right now, currently, unless Kambiz released a new version the last 3-4 days, does not currently allow for multiple channels in one project. So you can't really do this type of optimizations inside Lunar. You can still use the Quasar engine and Nova optimizer, but you have to write some scripts for it. But in this case, just to show how we can embed this in other tools, we'll use another optimizer, and we will be using the Quasar engine to calculate the response to the curves. I will talk next page about the Quasar document. Well, a little bit other first here. So now I run actually I use exactly the same Latin Hypercube setup in Insight. Run the step steer maneuver, use the same tool. In this case, I actually export 4 channels. The lateral acceleration, the roll displacement, and the roll velocity, even though I'm only going to use roll velocity. And I do go through exactly the same procedure. I fit the roll velocity inside Lunar. Actually came out with the best fitting. And remember, when you export this from Adams, it's actually going to come out in radians per second, which is the native solver units. You can convert that if you want afterhand, but I can live with it. So if we look at the workflow here, so the core is the Quasar engine, which is taking a script. In this case, I call it optimization 2S Quasar. this is gonna read my DOE setup, my X files, and my responses to Y files. And it also will read an XN file, input file, with just one row of data. And then gonna fit this parameter set to the curves and write whatever outputs I want to an output file. This one gonna be read by an optimization tool that then proposes a new set of parameters and changes the input file. Then repeat this. I'm using Heats and MDO because that's an optimizer I'm very familiar with and using it almost weekly. But you could use anything, and as I said, you can even use Nova here. You just have to write a script for Nova. All that. Setting up the Quasar script here. It has a very extensive command language. Originally looks a little bit confusing, but it's really well documented. What I'm trying to do here is I'm specifying my X and Y files for the absorbed power and for the step steer. So these are my original DOE setup and responses to the DOE. I specify an XN file, all inputs CSV. This is going to be tagged by Heats now. Then I run the prediction for the YN for the absorbed power using the kriging with the rest of the parameters specified. I call another Quasar function to extract all statistics on the response curve, the YN curve, and then assign the maximum value to a max value AP. So exactly the same thing for the step steer. Put this together in an array and write that to the output file. Once you've done this once, it's very easy to figure out how it works. Now in your optimizer tool, in this case Heats, I specify just the execution command is just called Quasar engine. You might have to add the path to it, to your path, your Windows path or your system path. But in most cases, that's already done by the by the installation. And then you specify which script you want to go to, and then you tell it to run in silent mode. That's going to save a lot of time. No problem to run this in parallel executions. I only have 4 parallel licenses with Heat, so I use 4, but otherwise this would run much quicker. And now in Heats, I go in and tag the input CSV to write a new set of parameters and read the outputs from the Quasar output. Assign those to variables and specify my objective and my constraint. Now I run the optimization here, I run 150 runs, which is suitable in Heats for 10 parameter set. This optimization took 75 seconds, a little bit slower than running Nova directly, but the reason for that is because I'm using parallel runs. I have to have termination criteria, and that's really looking at that the Quasar output file is written and contains values, and it takes about a second or less than, well, a tenth of a second or 2/10 of a second per run. So still very quick, and this allows me now to run very, very quick what-if situations. I can change my constraint. For more complicated examples, you can run different optimizers, you can change different constraints, you can change weighting between different objectives, run Pareto front optimizations in times you could never dream of in other cases. So here is really the conclusion from it. So I run actually 5 different optimization where I constrain the maximum roll velocity to 8, 7.5, 7, down to 6 degrees per second. And here is all the response or the factors. But more interesting is to look at the responses here. And our baseline their Lunar estimated absorbed power pretty close to the actual absorbed power. With no constraint, as we saw before, it was an 11% difference. When we start constraining this, what we in practicality does is that we're constraining it harder and harder. We're forcing the absorbed power to inside our base curves here. So when we go to the best curve here, where we constrain the roll velocity to 6 degrees per second, we have a very small difference between it. And of course, the constraint is also a constraint on the quasar or lunar side. So when we look on what Adams actually verified, it's a little bit higher. But again, also there, because we're forcing everything inside the original DOE, we now have only a 6 or 0.04 error, the final value. So I think I've been able to hold the time. So it's basically giving you an overview of how Lunar, Nova, and Quasar can be used in conjunction with each other or in conjunction with other programs. How you can use this technology to reduce the number of runs compared to traditional DOEs, and how you can get an understanding of parameter sensitivity. And let me, as a final thing, show you, if you don't believe how fast this is. So here is all my optimization runs. So I just asked Lunar to export this out. That's what I used. Let me go in. I have this same experiment. I'm gonna hide all curves there, clear imported curves. Select, instead of my original curve, I'm gonna select my verification runs with those, was it 7 or 8 columns? 7 different runs. And I say import this. Would have been enough to do an interpolation. Now it actually takes more time to import it. There you saw, from that I click this button until I have 7 runs done, it takes less than a second. And now I can go in and at any point here, for example, see how the sensitivity changes between the different parameters. If I make it bigger there. Oh, this point, for example, where everything steps up. So I think that was all I had.
Yeah, thanks, Jesper. Great presentation, great content, and thanks for throwing in the demo. I see a few questions that I've streamed in. If there are more, please let us know. And let me start going through the list of questions. So the first question here is, how does the nonlinearity in the response affect the amount of training data generated, right? So maybe Kambiz, you could start with that, and Jesper, if you could add on in your response. So Kambiz, the question is, how does the nonlinearity in the response factor into the amount of training data required?
Yes. Can you hear me? Is it okay?
I can. Yes.
Well, any nonlinearity which can be decomposed into sort of modes can be handled. So in essence, any nonlinearity which is not chaotic, which is not arbitrary, which is not random, can be decomposed on a series of let's say nonlinear but simpler modes, which we exploit in order to do the machine learning on them. We actually learn the behavior on those modes and not on the nonlinear signal itself. Once it is decomposed, it's more or less easy. The tough part is find the right decomposition, and there are tools in Lunar. The last tab, which is called user script, actually provides you a way of finding the best decomposition mode, and it does it automatically. So any nonlinearity can be handled. If there is a model, we can discover it. If it's completely arbitrary, then the answer would be arbitrary. Yes,
okay.
this one.
Okay, thanks. Thanks, Kambiz. Jesper, so the next question is for you based on your presentation. The question is, in your example of suspension design, there are only parameters considered with limits independent from each other. What if you include parameters like hard points of the suspension and take into account things like packaging constraints? Maybe it goes beyond your application, but yeah. So.
Yeah, but it's a very common problem, and that has much more to do with how you parameterize your Adams model than anything else. As I see this, and it's something we often run into, you don't want to change hard points independently. You want to move around an existing control arm, see what happens if I have a misalignment on it, or without changing the dimensions of the control arm itself. And that's more of a question for the developers of Adams Card than anything else, or being creative in how you do your parameterization. It's something that we're always fighting with.
Okay, makes sense. The next question is, and this is probably for both of you, Jesper and Kambiz. The next question is, Jesper, when you went through your presentation, you showed how you could improve the validation of the ROM through changing different solver settings. The question is, why did you not look at maybe changing your original DOE design or including more refinement in your training data?
I can do that. I can add more points, but if I don't think that these values or these fits are good enough, I would add another 10 points to my run, which would be fairly quick. But if we look, for example, on this curve here, it doesn't look too bad. I assume I'm still sharing, right?
Yeah.
So no, and then Lunar actually gives you its own DOE generator, where you even have an append to DOE. The only important thing, if you do this with an external DOE generator like Insight, is there is a risk that you add an additional point that actually coincides with the original points. And that would give you singular matrix in Lunar or in Quasar, really. Luckily, Lunar provides you with a script to eliminate overlapping points. To do that, so if you get an error for singular decomposition, just run that script and it will remove the 1 or 2 points that's overlapping. If you run the DOE tool in Lunar, you never have that problem. But then instead you have to build up a workflow from here into Adams.
Right. Okay, makes sense.
I'll just add one sentence. The sampling issue is central to any learning process. The requirement, which is most general, most important, is that it should be space filling. It has to cover all empty places of your space. The better you fill the empty spaces, well, the better you can somehow fit your model to. Now this, of course, is somehow opposing the number of runs, number of samples. In order to accommodate for that, we have developed solutions which can actually optimize an existing sampling in order to move samples from one position which there is already information available to another position where there is less information available. And as Jesper said, well, that is in the new version 3.4, which is actually out, Jesper. So you will be the first person to receive the better version, at least.
Thank you.
So we have solutions.
Yeah.
Right.
And that's one of the reasons to use the Latin hypercube, is that a minimum run of the Latin hypercube really has 1 point in each column and 1 point in each row. A little bit like playing Sudoku.
All right. So yes, but there's a clarification on what you presented. The question is, in the application that you presented, You went through a single training where the inputs were scalars such as stiffness, damping coefficient, and the output was the vertical acceleration of the or a output of the time series, right?
Yeah.
Yeah. Okay. There's a question on portability of these ROMs. How you showed how using Quasar you could connect these models to something else, but is there a way to export them out as FMUs or CLLs?
Yeah, I see those questions. There's actually a couple of questions from Stefano there. Hi, Stefano. So can we use this in real-time simulations, and can we export it as an FMU? Both cases, it should be possible. I have not tried it. In real-time simulations, yeah, definitely. You just need an API that goes in and samples it, because it will calculate everything much, much faster than real time. You see here, it calculated 7 curves over 20 seconds in less time than I can move the mouse from one point to another. So if you just can go in and sample it, and one application we are looking on is to really use this in controllers where we have run a whole bunch of DOEs from different starting conditions. And depending on the state, it would actually estimate different types of responses. That's one thing we're planning to use this technology for. Do you do it for an FMU? You just write an FMU wrapper. It should be possible.
Yes, that's of course possible. Quasar can do that. But we also have the version you are seeing here, which is behind Lunar, is what we call a non-intrusive ROM, non-intrusive version, and that means it's a wrapper around the solver. So you launch the solver every time you need a data point to be evaluated. Now we have another version of Quasar which can be encapsulated inside the solver. We already have a version of this for LS-DYNA, and we are working on Adams and Nastran to do that, where you can actually communicate directly with the solver, like an element. I mean, the whole suspension model, for example, can be considered as an element where the data, its behavior is encapsulated, and then Adams doesn't need to compute that every time, or the tire, or whatever. So there are a lot of this. This is really the advantage of this technology. There is a great simplicity of exchanging information with any solver or any other application. We also have application with gaming, which is also very interesting, because one of the issues in gaming is that they want to be more and more realistic. So they have the need to actually calculate the mechanics of the movement, and that is done via FMU or anything similar. Similar thing for ADAS systems. We can do the same thing. So the technology is very flexible to be integrated, encapsulated. That is.
Thanks, Kambiz. The next question is, we're almost up to time here, but the next question is, does a model for time series information, does it build a separate model for each time step and combine it? I'm guessing not, right? So are you building a model for every time step?
No, that would be a little bit cheating. Right. In some cases it's possible. For example, if your problem is static, you can do that, or if it's multiple loading cases, you can do that. But if it's real dynamic, well, the only way to do that is to do it for every time step, and it's a great effort. Then you might as well go and solve the finite element solution, because I'm sure it will be faster. But what we do, as I said, we have a spatial and a temporal decomposition lighting model analysis, which allows us to work on modes and not on time steps. So we work in a frequency domain and not in a time domain, which is a great advantage, which is also the reason why just by a click, Jesper can create 7 different responses. We can, if you just there's a tab there called Generate Range, Jesper. If you could just click on that. I don't know if you still have your screen open.
Yeah, so let's
50 runs. Yeah, just click on the. Just leave everything. Just click there. Yeah.
I'm gonna take one in the middle there.
Anyone. Now these are 50 runs, which are just simulated 50 runs. Now you can't do that if you follow time step by time step. Now the variation is small, but you can see how robust that particular solution is within the gray zone. You can see the gray zone, and this is something which is really fast because of those decomposition techniques and not time step interpolation.
Thanks, Jesper. There's a question on how is this technology integrated with FEM software, which I know is your kind of bread and butter. So, just quickly, Kambiz, if you could comment on that.
I didn't understand the question probably.
Yeah, the question. I'll read it out. How are the machine learning and ROM algorithms, I guess, in the context of what is presented today, coupled to FEM software?
What we have is actually that we have a coupling between FEM and machine learning. The only thing is that how do you couple this externally, like two executables communicating with each other, or one executable which is encapsulating the other one as if it was handling a submatrix, stiffness matrix, etc. There are many ways of doing that. Now, what is important is that this quasar technique is completely independent of each other. So the same technique, exactly the same steps, works whether it's mechanical, static, dynamic, thermal, CFD, acoustic, crash, whatever you want. And this is completely open to any finite element solution, or, as I said, to experimental data, because Lunar can also take as a knowledge base, as database, it can take experimental tests. Yeah, this is completely possible. Nothing stops Lunar to use as those gray curves you see there, experimental tests, or a combination of finite element and experimental, and we often do that, which allows us to have a actually augmented model. You can have a CAE model, which you have, I don't know, 10 possibilities to run, but then you have two tests, we combine them, we have 12, and those 12 are much more rich than if I had just one finite elements model, or you can combine multi-body models and finite element models. As I said, that solver block is completely independent. All we care about is this parameter set and the response set, and we find our way in that.
Okay, thanks, Kambiz. We are over time here. There are a few more questions which I'll answer offline, but that's it. Thanks for the great presentation, Jesper, and Kambiz as well. A lot of good information. I'll make the recording of this particular talk available, and if there are any other questions, please reach out to us, and we'll route them through Kambiz and Jesper. Thanks for your time.
Thank you, everybody, for listening.
Thanks.
Thank you, Manat. Bye-bye.
Thanks, Kambiz.